All right, good morning.
Morning. Morning. Morning.
All right, well, no, there's no ODP today. I'll post an ODP tomorrow morning, which will be due Wednesday.
When can we start on PA3 or PA2?
I'll probably post it later on in this week. Definitely by Friday. And then it'll be due a week from Friday. All right,
The C-stick one?
say again?
Is PA2 the C-stick one?
I think it's going to be a C version of the stick game, but it's going to be a slightly different version, different rules, different ways of handling errors, things like that. So you can get started on it if you want, but there's going to be a lot of details that that might be different from PA1.
I was going to ask you an interesting question about that because I didn't know that there was a standard stream called standard error.
Okay.
The other day when you mentioned it, would it be possible if I used some function like fscanf and I sent it the output, or sorry, fprintf, something like that, and see where you can specify a string to send it to?
Yeah.
But you send it to the standard error if you chose to do so.
Absolutely. That's exactly what people do.
Interesting.
So yeah, if you want to generate a message that won't be captured by like a redirection of standard out, you have printf it to standard error, and then it will show up on your screen by default. All right, so send me an attendance note. Let me know you're here. And I'm thinking what I want to do is run through really briefly just an example of some stick code and talk a little bit about general things I saw with the stick assignment. Then I want to go back to talking about C. And we're going to start digging pretty deep into C this week, including in particular how to deal with input from the user, both runtime inputs and command line arguments. So let me pop up a window here. So as an example, right? So this was my rendition of stick code. There are a lot of ways to do this, right? Despite my requirements on Bash syntax and the requirements of the assignment, there's a lot of ways to implement this. And I saw lots of implementations that were very different from this that were absolutely perfect. So I'm not claiming this is the best way. It's a fairly long implementation, 153 lines. Again, PA2 will get posted later on this week, definitely by Friday. So some kind of intro message. How many sticks would you like to play with? And I read a number, and then this is the kind of obligatory while loop. If the number is less than 15, you did not have to do this. This is just a little trick to see if the person put in a decimal number, but I didn't require that. All you needed to do was check to see if the number was less than 15, and if it is, print an error message and ask them again how many sticks, and don't forget to read at the bottom of the loop. No problem. We say a lot of stuff in this class, so it's hard to catch it all. All right, so then I print a confirmation message, and in general, this is useful when you're interacting with somebody who's running your program. You can give them confirmation, of what they've done. This is a speaking technique too when you're talking to a friend and you're trying to figure out, well, when are we going to get together, and what am I bringing and what are you bringing? So, when someone answers a question, you can say back, okay, I heard you say such and such, and it's a good way to kind of confirm. So I think that's what I was doing here. And then who should go first? U for user, C for computer. And then again, a standard loop while it's not U and it's not C, and you got to be careful of the condition here. This is while it's not this and it's not that. Say you got to enter a U or a C, get the answer again, and go back. And then, again, I just did another confirmation here. If it's U, I tell the person the user will go first. Otherwise, I say the computer will go first. Just making sure that, the computer and the user understand each other. And then, brief description of the instructions. Okay, each turn the player can take 1, 2, or 3, and go for it. So I show the pile of sticks. This is the old ODP, right? So, and then I decided to do this using that special approach where if the computer is going first, I'll do one computer turn first. And then my main loop will be user followed by computer, user followed by computer. So if the computer is going first, I can't go straight into this loop. So I do the computer turn first because it was shorter to code. So if the first turn is the computer, right? Say, how many sticks do you want to take? That's a variable called me. If it's equal to 0, I set it equal to 1. And then if the computer's going to take 1 stick, I say I take 1 stick. Otherwise, I say I take, however many sticks. And then subtract that from the number of sticks in the original pile, which was num. And since you're starting with at least 15, this is not going to end the game, so I don't need to check for an end of game here. And, I got a little block of comments here explaining what's going on in this chunk of code, which is the main loop does the user followed by the computer. But if the computer is going first, then we treat that here. All right, so the computer takes a number of sticks, and then we have the same old while loop that prints out the picture of sticks. And now we got our main loop, right? So this runs as long as the number of sticks left in the pile is bigger than 0. So there's still sticks to play with. So this is the user's turn. How many sticks do you want to take? There's our kind of usual if statement, and I could have done it like this. So if it's not 1, 2, or 3, I say that's cheating, and I ask them again how many sticks, and if it's still not 1, 2, or 3, I say you lose, and I exit. Otherwise, yeah, go ahead.
Out of curiosity, is there a limitation of how many ands in an if statement there have to be?
Not practically. I mean, if you tried to do 10 trillion, it would probably run out of memory, but no, there's really no limitation.
Okay.
Yeah. But if I was going to do a bunch of them, I would probably do something like this. Try to make it like line up so that it's easier to read, and you can continue bash statements by putting a backslash at the end. So now I could have, 50 of these, and it wouldn't be like all wrapped around weird on my window and so on and so forth. It would be like easy to see. So there's options. All right, so subtract u from the number of sticks. Num is my number of sticks. Show the new pile of sticks. That's our good old for loop. Check to see if the number is 0. That should probably be less than or equal to 0. And if it is, I can say u1 and exit. Otherwise, it's the computer's move. So again, find the number mod 4. If that's 0, set it equal to 1. Say I take 1 stick, or I take 2 sticks, or 3 sticks. Subtract it from the number of sticks in the pile. One more while loop to show the pile of sticks. And if the number is equal to 0, say I win. And that's the whole while loop. It goes from there back up to this. So this is very inelegant code, right? There's nothing very fancy here. You could definitely write a function for printing the number of sticks and probably cut the size of this down significantly. But you could write a function to see if this is a legal number between 1 and 3 and so on and so forth. This is very sort of straightforward, unelegant, but functional code with typos. And sometimes it's easier to write and work with code that is kind of straightforward, implementation of what's in your brain. And then if we were worried about other things, or if you were doing this in the group or something, you might go through and try to tighten it up, put these things into functions, put the whole stick pile display into a function or something, put it into a script.
Would you call this procedural versus functional? Like procedural would just be line by line by line by line, and then functional would be more of a separation of that?
Well, functional is actually a very specific term usually in programming, and it means something different. But I would say this is kind of monolithic, right? It's all one script with just a bunch of sequential code with some loops thrown in, as opposed to, I might say, modularized, where you sort of created separate pieces of your program and then put those pieces together. And that's what we're going to move towards, is doing more kind of modularization of code, breaking it into chunks and putting it together. All right, so a couple of things on PA1. Grading wise, so grades are posted in Canvas. I think everybody's seen those, and there's comments in there as to where point losses were taken and so on. But just some of the general things that came up. So we've already talked a lot about Git and about how your directory should be structured, right? CSE224, and underneath that is a PA1. Underneath 224 is a PA2 and a PA3 and so on, and each of those contain your code. So if your Git was not set up that way, if your file was in a different location, I mentioned that, but I did not take off points this time. If the name of the file was wrong, it was supposed to be STICK, 5 letters, lowercase. If the name was wrong, I noted that, but I did not take off any points. If the game let the person pick 0 sticks, that's a deduction, because that's an easy way to cheat, right? You can just keep taking 0 sticks until there's only 3 sticks left or fewer, and then you can take the last sticks. And that's a small deduction. When you play the game, you need to ask for a U or a C, and if you type in anything else other than that, it should, keep asking you for a U or a C. Case matters, right? So uppercase U is not the same as lowercase u, and so on. So I was looking for that. If it doesn't ask at all who goes first, and it just does, computer goes first always, or user, that's a bigger deduction. When you're playing the game, right, if you put in an invalid answer 2 times in a row, it should kick you out. So if it doesn't do that, that's a deduction. If it doesn't let you, correct a bad error and continue playing, that was a deduction. Almost everybody had their shebang in the first line, so that's good, but I looked for that, and if I didn't see that, that's a deduction. That's got to be there. Stick pile display had to be in a very specific format. Picture of pipes followed by your number in parentheses, no extra spaces, things like that. This is the kind of thing that if someone was going to grade this with an automatic grading tool, they would probably scrape for these pictures, right, and then parse those out, because that's a very easy, recognizable pattern. But I kind of effectively do that when I'm grading, right? I'm playing the game, and each of your games I probably played, 7 or 8 times minimum, and I'm going through and I'm visually picking up these things, right? And after a few hundred games, my mind is really tuned towards picking out those patterns. So this is important formatting. A few people decided to limit the number of sticks that you can play with. One person set a limit of 21, and you can play with 10,000 sticks, and that's a long game, but it's totally valid. There's no mention in the assignment of an upper limit, just that it has to be at least 15. A few people set the maximum to 15, and so that was another issue. So there were a lot of issues around kind of like translating what was in the assignment to what you wanted your program to do. Um, and then some of the other things were if something gives you a syntax error, so when you run this, if you just hit enter, it should not give you a syntax error. It should not assume you meant something. It should say give me another number. Same thing here. And then here, if you just hit enter, don't generate a syntax error and don't exit your program. Just say try again. So make sure you try edge cases, and coming up with edge cases to test your code is usually a bit of a challenge, right? That's part of coding, though, is being able to test and validate your code. A lot of businesses, have entire departments dedicated to that. And you would finish your code, you would do some testing, and then you'd hand it off to like a QA team, and they would do a series of maybe standardized tests. So being able to do some of that yourself is important. The commenting looked really good in most cases. People are putting in lots of comments, and people are indenting consistently and meaningfully, and that's fantastic. I've never been this early in a 224 class where even a few students were putting in good commenting and such, and almost the entire class seems to be on top of this. So that's fantastic. Keep doing that, because that's gonna just help you down the road. So those are the main things. There were a few other things here and there where it's not saying who wins or something like that. 270 burn commenting into your mind. Excellent. That was my goal. Cool. Good deal.
I ran into some error, by the way, for anybody that's using WSL.
Ah.
It might be a Ubuntu to Debian because I'm using an Ubuntu kernel, but I would have full permissions on my stick appear on Ubuntu, and I thought I had full permissions on the Debian server, but Nick wasn't able to properly execute my stuff, so be careful
Right.
with that.
Yeah, and we worked through that in office hours a little this morning, and there's definitely some kind of issue, and I don't know where the issue is, but changing the permission on a file and trying to push it to Git doesn't seem to get noticed if you're doing it from WSL. So yeah, and Python will burn indenting into your mind because it's mandatory, right? That's the curly brackets. All right. So any sort of lingering questions on PA1?
Have you ever ran into a situation where, you know how you have the $sign and then a word to call in the variable within that specific locked word? Have you ever had an experience where it's not just the $sign, but maybe something else?
What do you mean?
We were chatting in the Discord, and apparently somebody's code ran with it saying sticks instead of stick with the $sign, and we're all like, how is this possible? I'm curious.
I actually saw something like that where someone had a while loop, and I think they were trying to do while n was greater than 3 or less than 1, and they did not say $n, and it seemed to be working. And I wrote some test code and tried that myself, and it seemed to be working. And I honestly don't know why. Bash, like many things, is something where you try to learn how to do something, and there's a whole universe of things that are outside that understanding of Bash.
When I was trying to go through I had like an error through one of my loops, and I couldn't figure out exactly what was wrong. And so I was on Stack Overflow just looking at bash arithmetic, trying to figure out what was wrong with my arithmetic. Everyone was putting no $signs on their variables when using the $sign to parentheses, but when they're using it's like the expression function or whatever. The thing, they were all using the $sign, so I don't know if that has something to
gonna do with that?
So inside $paren, you can definitely get away with not having the $sign, and that's useful sometimes. But in a plain old if statement or a while loop, we try to put the $signs on there pretty consistently. But yeah, so here's an example, and I'm going to do this, but this doesn't mean that you're allowed to do this in your assignments. I still want to see the $signs. But, I can say something like n equals 5, and I can say if n equals 5, echo good, and it echoes good. And if I said n equal to 4, and I say if n equals 5, it doesn't say good. So, I mean, it understands that it should use the value of n here, even though I didn't put a $sign. But I'm pretty sure there's going to be cases where I'm going to get into trouble doing that. So I'm going to say go ahead and stick with a $sign. But yeah, I was surprised when I saw that worked. Yeah, I turned my face camera off. I'm not sure why. I didn't feel like dealing with it. All right, so let's get into C. That's the other sort of general main topic for this course is going to be C. So let's just hop in. All right, so let's start with a hello world. So for some reason we always put $sign include standard io.h, and then we do integer main, and then a printf statement. And this will give me some errors. So if I gcc hello.c, I get an a.out, and if I run that, it says hello. So not a big deal, not very exciting, but there's a lot going on in here, right? So let's start with compilation. So normally when we compile a program, we say gcc-o. And if you just say gcc-o and if you just say gcc name of the file, right, you get an a.out, and your executable is always called a.out. All right, so terminology. You have a file.c. That's what we call source code. Source code is just the code that you wrote that makes up your program. It's code written usually in C, Java, Bash, something like that, right? For C, it's all of this stuff, right? $sign include integer main, printf, all that kind of stuff. So that's source code. We compile that using a GCC command. And there's a bunch of things that happen when we say GCC, but the end result is what we call executable code. Or sometimes machine code. So source code is human readable, executable or machine code is machine readable. It's the ones and zeros. And if we just say GCC, we get a file called a.out. But it's pretty inconvenient if every time you compile a program, the executable has exactly the same name, because your previous a.out will be overwritten. So it's useful to put a switch on here, like GCC -o, and then what we list here is the executable name. So the name of the executable file that we're trying to create. And then your source code. File name. So a preferred way to compile my code would be to use GCC-O. So I could say GCC-O hello.c. And now when I do an ls, I've got my executable code hello, and I've got my source code hello.c. Now if I make a second program like stick.c, I can compile it and call the executable stick. And I still have my old executable and so on. So to run it, you just type the name of your executable, and it goes ahead and executes. Or depending on your setup, you might have to say / in the name of your executable. One thing to be really careful of, though, is when you do GCC-O, the thing right after O has to be the name of the executable file you want to create. Don't put anything else here except the name of the executable file you want to create. And here's a really common mistake that will ruin your morning. Right? Don't do that. Because what I'm saying is I want to call the compiler. I want to create an executable file called hello.c, and here's my source code that I want to compile. Well, that's backwards, right? So if I do that, I get a bunch of messages, and I say, oh yeah, I did the wrong thing. I should have done this. Well, I get more messages, and guess what? My hello.c has disappeared. Right? So what I did was I tried to compile an executable, which doesn't work, but I said, put the output of this compilation into hello.c. Well, the first thing that GCC is going to do is delete the current hello.c so that it can create a new one. That's why my source code disappeared. So if you're working in multiple windows, you know, I've still got my hello.c over here. Hey, it's back. Magic. Right? If you're putting backups somewhere, you can copy from a backup. If you're working with Git, you can go to Git and you can download the last version that you pushed. Otherwise, you're typing your program back in from memory. Where did the .out go for the hello executable? What .out? I don't think I've mentioned a .out.
It's the you used the -o, so the output was not a.o. It was hello.c.
Right, so the -o switch is saying call the output file hello. That's what the executable is going to be called. So if you just say GCC, here's basically the effect of what you're doing. GCC-O a.out file.c. Right, if you don't type a -o anything, then it names your output file a.out. Yeah, thanks whoever answered that. All right. So what is this executable file, right? If we look at this hello file, it's computer speak, right? On this system, it will always start with something followed by ELF. That's a tag telling the system this is an executable file. But it's mostly unlegible, although there's a few things in here that we can read, libc.so.6 and so on. And if we look further in here, we'll probably find the word hello somewhere. This is only 4 lines, but these are very big lines. So there's something that says Ubuntu 16.04 and some other stuff. But it's binary code for the most part. So we can look at that binary code with something like XXD and see, you know, the hexadecimal versions of everything that's stored in that file. And there's some stuff that's readable, you know. But most of it's not meaningful to us, but meaningful to the CPU when it executes it. Hey, look at that. There's the word hello. That's the argument that's going to be passed to printf at some point. All right, so what about this include business? Let's look at the source code here, because this is how we write a hello world, but what does it mean? So number sign include, standard io.h. What is this printf function? This is something that generates output to standard out, but basically to our display. And it prints, you know, whatever this thing is in here, but if I have a %d and then an integer variable, it will convert the value of that variable to digits and so on and so forth. This is an amazing function. It's a really big function, super powerful. But what is that function? It's not described anywhere in here. I didn't write printf. I'm not planning to write printf. So when we say GCC, GCC knows about libraries of certain functions, and it knows in particular where the printf function is. And it will pull in the code for printf so that our program can be made executable. But before we get to the point of actually trying to finish building an executable, we need to compile this code, convert it into a machine-readable form. And remember, there's this notion of function prototypes. Anytime that you use a function in C, you've got to describe what that function looks like, what the inputs are, what the outputs are. And I didn't prototype my printf function. And so if I don't have this include statement, and I try to compile this, it's going to say incompatible implicit declaration of built-in function printf. There's a warning at line 3. I got like 4 or 5 lines of errors. But you know, one of these is a note, include standard IO, or provide a declaration of printf. So it knows standard IO is missing, but it's not going to assume that that's what I wanted to have. It's just going to tell me, hey, go ahead and put in standard IO. So I'll put that in, and then when I try to run this, it should work fine. So what does this include doing? It's basically providing what's called a declaration of a function, right? What we call a prototype. So there's a directory /usr/include, which has a bunch of .h files in here, including, guess what, stdio.h. And this is a small file of 1,000 lines that are basically included in the beginning of your program. So I say, you know, include standard io.h, and bingo, 1,000 lines of C code take the place of this statement. And it's these 1,000 lines that come in. So there's some copyright information, there's some setups and so on. There's some other files that are included, and so on. But somewhere through all of this, there will be something that defines what a printf is. So printf is an external function. It returns an integer. It takes a constant character array of this type, and it can have multiple arguments, a variable number of arguments, right? This is the line that stops this error message from appearing when I try to compile. But you know, you don't want to type all of this into the beginning of your program every time that you write a C program. That would be a lot to type. So instead, we just say, you know, include this file that contains all of this information. That's what this thing does. And if you're going to do something else, like you're going to use the malloc function, you have to include a different file. If you're going to use string functions, you have to include string.h. So there's different files we need to include. And these angle brackets say, hey, look in /user/include, right? Look in this directory for the file that I've named. If I said include quote, standardIO.h, it'll tell me there is no, oh, let me come back. It'll tell me I can't find standardIO.h. Oh, never mind. So quotation marks say look either in my current directory or look in user include, but use angle brackets. But if I wanted to include a file from my current directory, I would use quotation marks, and it'll tell me, hey, there's no such file in this directory. But for now, stick with angle brackets to include these standard files. Same thing if you want to do math, you have to include math.h and so on and so forth. All right, so what about main? Main is a keyword. It's the name of the main function, right? Everything we write in a C program is a function. Functions basically have a return type, they have a name, they have a list of 0 or more arguments in parentheses, and then they have a body enclosed between curly brackets. Well, I have a function here called main. I could call this something else. I could call it my main, and it will still compile, but it will not build an executable, because in order to build an executable program, you must have exactly one function named main. And when I'm trying to build my executable, it says, hey, I can't find main, undefined reference. So there's nothing wrong with having a function called my main as long as you also have a function named main. And so, I mean, I could do something like this. And this will compile and run just fine. And it'll just say hello. And you know, I've got another function here called my main. I don't happen to call it anywhere. But you got to have a function named main. Right? That's the minimum requirement. All right, and then this integer business. So functions return values unless we say void. And so if I wanted to return a value here, I could say, you know, return 15. And I can run this, and it runs. So what is this returning, this return 15? Well, for a main program, if I return a number, that's what's called the exit value of the function. Right? If it's my main function and I return 15, that's going to be the exit value of my whole program. And in my program, I've run it from bash. Anytime that I execute a bash command, I can see what value that function returned. It's stored in a variable called $question mark. And if I echo $question mark, guess what? It's a 15. And if I change this to return a 7, and I run my program and I look at $question mark, it's a 7. So we can get information back from a C program to our shell script by looking at the value of this variable $question mark. But be careful, $question mark is always the result of the last command. So if I look at $question mark right now, what's it going to be equal to? It's going to be a 0 because my last command was an echo statement. And echo returns a 0 if nothing weird happens. But if I go blah, 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 and I look at $question mark, it's a 127. Why? Who knows? But that's what it decides to set this to. And if I try to remove blah, 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 and the file doesn't exist, and I look at $question mark, it's a 1. Because the RM program, the main program of that, returns a 1 if you try to remove a file that doesn't exist. So it's kind of up to, you know, whoever is writing the program to decide what the return value will be. Usually we don't care, we just return from main. We might just make it void and return, or we might not put a return statement at all. But if you want to get information back, you can do that.
Seems like it would be great for debugging.
Definitely great for debugging. And it's pretty typical, you know, when you're writing a program, if you have multiple conditions under which you might exit, you return with a different code for each condition. And now if I call this from a script, I can say, okay, so, you know, status equals $? If it's 1, you didn't have the right arguments. If it's 2, you tried to take the square root of a negative number. If it's 3, you know, it was Tuesday or whatever. So you can pass back information as you choose. All right, the last thing I want to mention about this is kind of what GCC actually does. And you know, usually it's just GCC file name or GCC-O output file name. But there's actually a lot of stuff going on. So we've got, you know, file.c, and when we say GCC, we end up with an executable file. And let's just suppose we're going to call that file. But really the first thing that happens is your C program gets turned into an assembly language program. And so this is usually what compilation does. It turns your C code into assembly language code. And then your assembly language code goes through what's called an assembler. This is like, you know, the assembler in 270 when we're in MP Lab. And this creates what's called an object file. So this is assembly code.
But we're about to get into linkers.
And we're going to get into linkers in the next arrow. So we create a file.o, that's the object. This is the binary version of your C code. It's the 1s and 0s that represent the instructions, the opcodes, and the operands to implement what your C program says you want to do. But it doesn't include things like printf, square root, cosine, fgets, all of these functions. So that needs to get linked with libraries that contain these other pieces. So this goes through something called LD. That's a loader. And that creates your executable file. And we don't usually worry about these things. We just say GCC and it goes from the beginning to the end. But in reality, you know, at least in effect, all these steps take places. Now, does it actually create a .s file and call the assembler? Not necessarily. But these steps need to happen somewhere. And so for example, if I say gcc-c hello.c, that says go as far as my object file and stop. So if I say gcc-c, that will take me to my file.o, but it won't go any further. So now if I look, I've got a file.o, hello.o. And you know, it's a fair bit smaller than my executable program, because it doesn't have all the extra stuff to, you know, call the print program and so on and so forth. And I can't execute that. It's by default not executable. If I changed it to have an executable permission bit, it's still not going to get very far. Right? It's smart enough to know that's not actually an executable file.
Quick question.
Yeah.
Is there a way to stop it when it gets to .s?
Yeah.
Read the assembly?
So do a GCC, I think it's an uppercase S. And let's do hello.c. And so that leaves me with a hello.s. And if you look in that, now you got good times. So there's assembly language code. So my laptop has an Intel processor, so this is x86 code. if you do this on a Raspberry Pi, you'll see totally different looking code because Raspberry Pis use an ARM processor. And so you'll see ARM assembly language. But this is x86 assembly language. And there's, a move, long word, I believe. There's a call to a function called puts. That's how printf works. And there's another move, and there's a pop and a push a quad word, move a quad word. So you can do assembly language development like this. You can take a program, break it down to a .s file, and then go in and look at the assembly language code. And we can kind of tweak this. Let's change the assembly language code, and now let's say gcc-o new, and let's just compile that assembly language program. And I've got a new program that I basically built from assembly language. So you can have lots of fun playing with this.
Wow, I can see it now. That's awesome.
So GCC-C gets you to an object but doesn't go any further. GCC-uppercase S gets you to the assembly language. And assembly language is fun. x86 assembly is fairly complex. It's got thousands of instructions, and you really kind of need to understand the sort of framework into which your assembly language code is going to turn into an executable, because half the code is things like defining sections of your program and directives like this. x86 may be a little more easy to understand. It's a simpler instruction set. It's a RISC machine, and so on. And there's C compilers for MPLAB, right? And you can compile your C code into PIC assembly language, and that's another fun way to look at some of this stuff. All right, so that's some of the higher level view of what's going on when we compile a C program and so on. So the next thing is to start digging into the language itself. So send me an attendance note, because we're close to the end of the class. Send me a ping, let me know you're here, and let me tell you what we're going to talk about next. So basically output and input. And output I'm not going to worry about too much first, because mostly we say printf. And printf gets most of what you need to do, but input is going to be interesting. While you're running a program, you want to get information from the user. And in Bash, we can use a read statement, for example. But for a C program, mostly when we get input, what we're going to do is we're going to use a function called fgets. And fgets will basically let a person type in a line, hit enter, and we can read that line into a variable, usually a character array. And so this will be useful for ingesting, right, for taking in a line of information from outside. But sometimes, once we've got this line of information, we want to interpret it. We want to parse it. This might be, a number that the person typed in, like we said, how many sticks do you want? And they typed a 2 and a 1 and they hit enter. Well, when we call fgets, what we end up with in memory is what we call a string. It's a sequence of characters. In this case, it would be the character 2, followed by the character 1, followed by our null terminator, something that marks the end of our input. We need to somehow change that into an integer whose value is 21. So that we can say, let's print out 21 sticks or whatever. So there's a parse step where we need to take what the person typed in and interpret it somehow. And this is going to be mostly done with a function called scanf. And we're going to spend we're going to spend a good chunk of tomorrow, but we'll come back to this throughout the term probably, just dealing with this idea of fgets followed by scanf. But whatever you know about doing input in a C program, if it's different from fgets and scanf, I'm going to want you to put it aside. In particular, there's a function called gets that you never ever want to use. Now, it's not actually as dangerous as people say, but if you're in a job interview and you write a piece of code on the board with the gets function, you've lost the job, right? It's a trigger point for people. So we're always going to use fgets instead of gets, and we're going to use scanf to parse what we ingest. And we're going to avoid using just plain old scanf, and we'll see why. But we're not just going to use scanf. We're going to use fgets followed by scanf. So we'll go through the details of what all this means tomorrow. We'll go through some examples. We'll look at why you can get into trouble using scanf and how you can use scanf and fgets to avoid trouble. And then we're going to talk about command line arguments, the whole argc argv business. So that'll be our drill for tomorrow, and I'll post an ODP that lets you exercise some of those things. All right, cool. Have a good one. I will see you next time.
Thank you. Have a good one.
Thanks, you too.
Thank you. Have a good
Have
one.
a good day.
Great day.